Paul Erdős, born on the 26th of March 1913, is a renowned Hungarian mathematician. Born in Budapest, both his Jewish parents were mathematics teachers, so left alone most of the time at home, he learned by himself how to read at the age of 3 by reading mathematics texts that his parents left home. At the age of only 4, Paul could square 4-digit numbers and calculate, given the age of a person, the numbers of seconds they have lived, making him a math prodigy. After graduating from the University of Budapest with a doctorate in mathematics, for which he didn't do all the courses, he just skipped right away to the doctorate, he moved to the USA to escape the Holocaust. Living most of his adult life a homeless lifestyle, he never stayed 6 months at the same place and kept his belongings in a simple suitcase. So in his mathematics devoted lifetime, he wrote 100 and 500 mathematic papers and collaborated with more than 500 mathematicians, a number that is yet to be beaten. It's because of all those collaborations that these mathematicians worked on so many problems. He moved one place to the other to collaborate with other mathematicians on different mathematic topics and then wrote paper about them. His whole life was devoted to making papers. So Paul Erdős was more of a presenter and problem solver than an expert of new mathematics. Now, he worked in different spheres of mathematics, such as discrete mathematics, graph theory, number theory, mathematical analysis, approximation theory, set theory, and probability theory. Of his lots of contributions, 2 work especially stand out: the development of Ramsey theory and the application of the probabilistic method. So we're going to talk today more about the Ramsey theory, and we're going to go more in depth. So this theory focuses on the appearance of order in a substructure given a structure of a known size. A typical result in Ramsey theory starts with some mathematical structure, for example a square, that is then cut into smaller pieces. So the question is, how big must the original structure be in order to ensure that the smaller pieces has a given interesting property? So for example, let's take the question here: what is the smallest number of people needed in a room to guarantee that either 3 people know each other or 3 people are unknown to each other? What is your answer? Well, we're gonna start, for example, by 5 people in a room. So green lines are people that know each other, and orange line are people that aren't known to each other. So let's draw the sides green, for example, and just the other connection orange. So here, the goal is to make a monochromatic triangle, which is a triangle of a single color. So here, if we take the side, so we have 1 green line and 2 orange lines, so it is not a monochromatic triangle. And no matter how we color these lines, we cannot have a monochromatic triangle including a side in this figure. So 5 people in a room is not the answer of our question. So let's move up to 6. 6, the hexagon, is the answer for this question. Spoiler alert. If this people is unknown to this and this people, well, we can have a square here. No, not a square, a triangle that is made out of all green lines. So that is a monochromatic triangle including 2 sides. So it is indeed the answer. And no matter how we color the sides, no matter how we color every line, we are assured that we'll have some monochromatic triangle. Thus, it guarantees us that in a room full of 6 people, at least 3 people know each other, or 3 people do not know each other. So this is what it's all about. This is the Ramsey theory at its simplest. So now more complicated, this theory states that the smallest number n, such that every 2 coloring of kn, so in this example green and orange, contains a monochromatic clique of order S or T. So in our example, it will be represented at R3, 3 is equal to 6. So 6 is a Ramsey number, and there are a lot of numbers that are yet unknown to us because they're just too big or whatever. Now this theory is used and applied in multiple fields like communications, information retrieval, and decision making. It's it's used a lot in computer science and a lot of complicated stuff that I can't explain to you because I couldn't even understand it myself. But it's used a lot by computers and a lot of spheres. So finally, I'd like to end it with a famous citation of Paul Erdős, our mathematicians. So sometimes you have to complicate a problem to simplify the solution. So I hope you liked the presentation and I hope you learn more about the famous mathematician Paul Erdős and the Ramsey theory.